So, so far we have been talking about writing CUDA program and use the NVIDIA C compiler to essentially, compile the code into two paths. One is the host path, where the code is eventually going to be compiled with either the Intel compiler or the GCC compiler. And the other path is the device code, which includes the kernel and all the functions that the kernel calls. And that path is going to be split into the device path, which is eventually going to be compiled and assembled into the GAD binary code. And these two will be linked together by the runtime by the NVIDIA runtime, and all the communication will be between the two pieces of code will be done by the driver code and the library, the data transfer library. So now, the picture that we're showing here is the fact that the C compiler that generates the NVIDIA GAD code is actually going to generate something called PDX. And this code, you can actually essentially look at this piece of code as a virtual machine code, almost like x86 assembly code. Okay, not exactly the same, because the code will actually be optimized and rescheduled a little bit at runtime. Okay, so there's still going to be a little bit transformation underneath, but it's really close. So just like in x86, when people want to write high performance code, sometimes they just use hand to write x86 math library and so on for really high performance code. You can also choose to write library code in PDX. And I would not be surprised if some of the high performance NVIDIA library code was actually handcrafted in PDX. So PDX is really represents parallel thread execution. PT and rather than PDE, they use the second vector, so that's PDX. It's based on a virtual machine and instruction set architecture, and it actually exposes all the execution resources. Okay, and what's your name? David. As David said, there's even a PDX manual for CUDA 1.0, which is a very good thing, by the way, because last semester when we taught this course, there was not a manual, so essentially people have to kind of guess things a little bit, and we talk about things a little bit. So it should be a lot easier this time. So what is this? It's based on the instruction set architecture. It gives you opcodes, well-defined opcodes, and it also specifies all the register operands and so on, in the program. And there's a translator that will translate PDX into the real binary code that NVIDIA would not want you to touch, because that real binary format is something that they actually will be changing from generation to generation. So this is something that that is a little bit different in terms of compatibility compared to the PC architecture. The Intel architecture is such that you should be able to take the executable from one generation and just run it on the next generation on a bare hardware, and it should just work. Okay. Whereas in the GAD series, you will be able to take PTX code and run it on the next generation, and it will work. But if you take the exact binary of a generation and take that to run on the next generation hardware, chances are it will not work. Okay, so this allows NVIDIA to be more, to give it more latitude in terms of some implementation details going from one generation to the next generation. Okay, and in that respect, it's a little closer to the Microsoft, the Microsoft bytecode or the Java bytecode in that sense. But the PDX code is actually a lot closer to x86 in terms of the instruction semantics and so on, that they don't go through a heavy-duty interpreter or just-in-time compiler just so that you can execute the code. The code itself is actually very simple and very close to the hardware. That just doing some minor adjustment, at runtime, they can pretty much execute the code on their hardware. So, the driver implements the virtual machine, and it's coupled with the translator. So when you launch an application, CUDA application on the hardware, really what happens is the command will actually bring out that translator, and that translator will quickly go through the PDX code and make whatever little changes that it needs to do and generate the real binary, okay? And then the binary runs on the bare hardware. Just to give you a little bit intuition about what the PDX code will look like, if you start with the CUDA source code, the CUDA source code will have, let's say a float 4. This is the vector format. Okay, so ME gets GX, element GTID. So then you do an addition of the various dimensions of the elements. You add a y dimension, multiply the y dimension and z dimension, and accumulate that into the x dimension. So this is just a contrived piece of code. So if you look at the PTX code, it's going to translate that first array load into variable into a array access and into various destination registers. Remember what I said, in the real hardware, when you have these multi-dimensional array vectors or structs, even though in the source code you would just do a variable assignment, but at runtime, in the PDX level, you will need to assign one register to each of the elements or the fields that you're loading. So these reflect the 4 registers that the compiler assigned to hold each of those 4 dimensions of the vector. Okay? And then this is the address generation for the array. So that's a load instruction. It goes into the global memory, and it's a vector load, so the hardware knows that there are 4 elements involved, and then the size is a floating point 32 bit floating point. So this is an opcode that tells you what you need to do to the address, and then each of the dimensions will be placed into a destination register. So for this instruction, you will use 1, 2, 3, 4 floating point registers, right? So just by looking at these numbers, you know how many registers are being used by the PDX code. And then you will do a floating point multiplication add that will do the multiplication and accumulate that variable into the, you will do the multiplication of F5 and F3 and accumulate that into F1. So this is one multiplication and add instruction. And this is the reason why NVIDIA will tell you that, there are situations where you can actually issue 2 instructions per clock cycle. Not 2 instructions, but 2 floating point operations. In one instruction issue slot, you will be issuing 2 operations, 1 multiplication followed by 1 addition. So if you have a piece of program where you can just do floating point multiplication at every clock cycle, you'll end up having 2 floating point operations per clock cycle out of every SP. Okay? So that's how you can calculate the quote-unquote peak performance of these chips. Whether or not you can do that all the time is a different story, but that's a peak performance of the chip. So just to give you a little bit more sort of background about how to read PDX code, let's say you have a piece of CUDA code, which is a CUDA function. Okay, so this is a small piece of CUDA function that does some calculation and do some square root and so on. So this is, this represents a kind of a little, floating point library function. And so when you the compiler compiles this function, it will generate the PBX code on the right-hand side. And it will generate a bunch of these, essentially generates a bunch of these, floating point registers and, all the multiply, add, and so on. And so, at some point, this thing, square root, appears to be a function call, but it is really intrinsic. Okay, it means that there is an instruction in the hardware that directly executes this functionality with high efficiency. So the compiler is smart enough to translate that square root instruction into a square root function into just a single instruction. Okay, and this will be very clear when you look at the PBX code. A lot of these trigonometry functions, square root functions, and so on are actually translated into single instruction. Okay, that's actually where a lot of your performance will also come from, not just from parallelism, but from very low latency, high throughput, floating point function implementations. Now, if someone calls that function, let's say you have a kernel code that calls the function. Okay, what happens is that that function is actually going to be inline. Okay, into the caller, so that instead of doing a function call in the PBX code, what happens is you will actually take that function all the way into the sink. And this is the reason why in CUDA you cannot use recursive call on the device side. This is one of the reasons. Because if you have a recursive call, you will be calling that function again and again and again. And the compiler will not be able to tell how many times you can actually inline that function call. Make sense? And that's another reason why, that's also a reason why in CUDA you cannot write device code with call through pointers. Because the compiler may not be able to figure out which function to inline. Okay? Now, you cannot also use variable parameters, because whenever they take a piece of code and put that into the caller, it needs to know how many registers it's going to use. Okay? So all these constraints are really there to enable a very high performance implementation that essentially will take all these function bodies into the caller, so that you don't pay the procedure called overhead and so on in the parallel execution. Okay? So if you look at this, during the loop, when I call interaction with these parameters, what happens is I'm going to actually take those variables, and like this SX is actually a shared memory. SX is in the shared memory, so we will actually do a shared memory access and put that into a floating point parameter, floating point register, and then this register is actually going to be hooked up with a piece of code that we saw before, which is the first parameter, this thing, okay, 15. So the compiler will actually inline the code and line up all the registers so that the code will execute smoothly with the caller code. So if you look at this piece of code, you say, okay, I have a lot of subtraction, I have a lot of multiplication, add, I have, add, multiply and add, and so on, right? But I don't have loads. On the other hand, oops, next one. In the caller code, I have this load here, right? I have the load here. So these are the different instruction mixtures that you're going to have, and you can actually just calculate from the mixtures that what's the absolute highest floating point calculation rate you can get. because if you have two loads and let's say two floating point computation, then the best you can do is half of your peak floating point rate, because those two loads will also take cycles to go through. Okay, so the mixture immediately gives you a fairly good sense of what you're not going to get beyond certain level of percentage of your peak performance. Okay. So another thing that I usually talk about is, let's say if you have a low latency load, okay, in this thing, and then you have the function body. Once you're in line, you can start to move some of the computation in the function body into the load, next to the load, so that you can start to tolerate latency better. That's another reason why the inline is function bodies, because now you have typical. You have the loads and the compute from different function scopes that are all mixed together, that you can do some of the scheduling better.